Good afternoon, this is Dr. Pradhan here. Today we will discuss the concept multivariate econometric modeling. In fact, we have discussed this concept last class little bit. So, today we will continue from that particular point of. So, the basic framework of econometric modeling means multivariate econometric modeling is that. So, we have a system where there are dependent variables y, which consist of y1, y2 up to yn, and corresponding variables are x1 say x11, x12 up to x1n, then x2 consists of x21, x22, x2n. So, continue. So, xk is equal to for xk it is nothing but xk1, xk2, xk2 up to xkn. So, that means we are targeting here a model, econometric models, where there is one dependent variable we denote as y, and there are several independent variables, that is here k number of variables are on the other sides as treated as a independent variables. So, now we like to see how is the setup and structure, the complexity, the strategy of this particular multivariate setup, where there are k independent variables and one dependent variable exist. So, the basic framework is like that. Before we go to proceed means to discuss about all these details about multivariate econometric modeling. So, what I will like to represent here. So, here the basic framework of multivariate modeling is like this: y equal to beta 0 plus summation beta I x I equal to 1 to n. In fact, this particular case it is equal to k, then plus u. So, this is the starting point of multivariate analysis. So, what we have to do? We will simplify this one. So, this is equal to beta 0 plus beta 1 x 1 plus beta 2 x 2 plus beta 3 x 3 plus beta k x k plus u. So, these are this is the basic format of multivariate modeling. So, now before we go for estimation, so obviously by standard rule you have to know certain things, or you have to assume certain things, so that we can able to go for this estimation, prediction and forecasting. So, the standard procedure is that, as usual, we have to apply OLS technique, because this is the standard technique through which you will get the original estimated models. Of course, we can apply double weightage least square methods, GLS, generalized least square methods, maximum likelihood estimator methods. So, in the meantime, we are not discussing any methods here. So, from the beginning, so we are discussing each and every modules through OLS technique. So, we also here present the OLS technique. So, later on we will discuss little bit about OLS technique, WLS technique, GLS technique, or maximum likelihood estimators. So, in the meantime, by using OLS technique, we like to know what is the shape and structure of econometric modeling. Even if you apply GLS, WLS and maximum likelihood estimators, the structure is more or less same. Of course, the path is a little bit different. So, here the standard assumption is that your E of error term must be equal to 0. That means, if you apply OLS technique, so before applying OLS technique, you must have standard assumptions, and on the basis of that standard assumption, you have to estimate the models, and later on the standard the assumption has to be verified. If not, then we have to continuously redesign, restructure the model till you get the best fitted model, which can also satisfy the following OLS assumptions. So, first standard assumption is that E upon U equal to 0. So, then covariance of Ui Uj is equal to 0. So, the then third is the covariance of Ui Uj is equal to sigma square u, and in this case I not equal to j, in this case I equal to j. So, this is the, if that this is not satisfied, then it is the serial correlation problem or autocorrelation problem. So, which in fact we discussed earlier. So this is, if not exist, then it is called as a heteroscedasticity problem. Heteroscedasticity problem. Okay, this is heteroscedasticity problem. And fourth assumption is that covariance of u and x must be equal to 0. Okay, and fifth assumption is that correlation or covariance between x1 x2, okay, equal to, or correlation between x1 x3 or equal to correlation between x2 x3, like this. So many pairs you will find. So it must be continue is also equal to 0. Okay, so this particular structure is called as a multicollinearity problem. Multicollinearity problem. Okay, so then of course the obvious standard assumption is that your n should be substantially greater than equal to not equal to greater than to k. Okay, greater than to k. So n represents number of sample and k represents number of dependent number of variables in the systems. Okay, so last but not the least, model must be correctly specified. So last but not the least, model is correctly specified. That means before we apply Wallace technique to this multivariate mathematical model to get the estimated model, so we have to assume certain things. These are the following assumption. On the basis of this assumption, we have to take the, or we have to estimate the multivariate regression model. So how do we go for that? So this is this particular structure is y equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta k xk. Okay, so this is how you have to proceed. All right, plus of course u. All right, so that means if you will put it in a particular format, then the structure will be like this. This is x1, this is x2, this is x3, and continue, this is xk. Okay, so the structure will be coming like this. Okay, so this particular structure is coming like this. So followed by, this is the beta 1 coefficient, this is beta 2 coefficient, this is beta 3 coefficient, and this is beta k coefficient. Okay, so by default there should not be any correlation between x1 and x2, x1 x3, x1 xk, x1 x2, x2 x3, again x1 x3 and x1 xk. So this is how the model is fitted here. So our objective is here to know this particular items. Okay, this particular item, that means we like to know what is the estimated values of beta 0 head, beta 1 head, beta 2 head up to beta k head. So now how do we proceed? So as usual, the way we have discussed in the case of bivariate setup and trivariate setup, the following setup can be also apply here to get this estimated model. So what is this exact structure here? The exact structure is that we have y equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus up to beta k xk plus u. All right. So now this is the true regression models. This is called as a true regression model. So let us assume that the estimated model will be y head equal to beta 0 head plus beta 1 head x1 plus beta 2 head x2 plus beta k head xk plus, obviously there is no plus, so beta k head xk. Okay, so these are the means this is the estimated model. This is the estimated regression model. So we have a original regression model, then we have to assume a estimated model, then by the way we have to make a difference and we will get the error component. So error is the difference between y minus y head. So which is nothing but y minus beta 0 head minus beta 1 head x1 minus beta 2 head x2, okay, minus beta k head xk. all right. So now what you have to do here? So here we have to minimize the error sum. So summation e squares I equal to 1 to n is equal to summation y minus beta 0 head minus beta 1 head x1 minus beta 2 head x2, okay. So minus beta k head xk, okay, I equal to 1 to n, okay. This is whole squares. So this is the original setup for this OLS techniques. So from this the new dimension will come up. So that means we have to go by this optimization principles, that is to minimize the error sum square. So that is nothing but we have to, that means we have to minimize the error sum square with respect to beta 0 head, beta 1 head, beta 2 head and up to beta k head. So by default when we will apply the minimization rules, so d summation e square by d beta 0 head equal to 0, d summation e square by d beta 1 head equal to 0 and continue like d summation e square by d beta k head must be equal to 0. Okay. So this is the first order condition. Of course, there is a second order sufficient condition. So we are not going so much details because it is not a mathematics completely. So here with the basis of the first order necessary condition, we have to get the process, okay, done. So now, so what is the structure? The first step is to have the partial differentials. So d summation e square by d beta 0 head is equal to 0, d summation e square by d beta 1 head is equal to 0, then d summation e square by d beta 2 head is equal to 0 and continue. So finally equal to d summation e square by d beta k head equal to 0. Okay, this is how it is all about means the process of the standardization. So now what you have to do? So we have to proceed for the next step. So how will we proceed for this next steps? So this is how. So now that means what is d summation e square? D summation e square by d beta 0 head is equal to summation 2 summation y y minus beta 0 head minus beta 1 head x1 minus beta 2 head x2, okay, minus beta k head xk, okay. So into minus 1 is equal to 0. Similarly, we have to go for d summation e square by d beta 1 head. So this is 0. So d beta 1 head, d summation e square by d beta 2 heads. So like this, d summation e square by d beta k head. So now if we will simplify this particular, so it will continue like this. So now let us assume that this is the second step of this particular process, means a second step of this particular first structures, means that is the first order necessary conditions. So in the step 3, what you have to do? We have to simplify this particular equation, then we will put in a simultaneous equation. So that simultaneous equation will help you to get the estimated values of beta 0 head, beta 1 head, beta 2 head and up to beta k head. So now if we will simplify this particular equation, so how do we go for that? So now it is nothing but summation y equal to n beta 0 head plus beta 1 head summation x1 plus beta 2 head summation x2 plus beta k head summation xk, okay. So summation x1 y is equal to beta 0 head summation x1 plus beta 1 head summation x1 squares plus beta 2 head summation x1 x2 plus beta k head summation x1 xk, okay. It will continue, okay. So then summation xky is equal to beta 0 head summation xk plus beta 1 head summation x1 xk plus beta 2 head summation x2 xk plus beta k head summation xk squares. Okay. So, this is how you have to proceed subsequently. So, now we have to simplify this particular structure to get this beta heads. Okay. So, now by the way, so what you have to do? So, if you will go by this particular process, then beta 0 head will be like this. So, summation y, then summation x1, then summation x2 up to summation xk. Okay. Then summation x1y, then summation x1 square, then summation x1 x2, then summation x1 xk. Okay. So, then summation x2y, summation x2 summation x2y, summation x2 squares, then summation x2 x1, then summation x2 squares, summation x2 xk. Okay. Then it will continue. So, whole divide by n summation x1, summation x2, then summation xk. Okay, divide by n, summation x1, summation x1 square, summation x1 x2, then summation x1 xk. So, it will continue up to summation xk, then summation x1 xk, then summation x2 xk, then summation xk square. So, this is how the structure. In the last part, this particular structures, it will be summation xky, okay, then summation x1 xk, summation x2 xk, okay, summation xk squares. Okay. So, this is how the first beta 0 head. So, we will get beta 0 head is this much. Okay, this is the beta 0 head. So, similarly we can have also beta 1 head. So, in the case of beta 1 head, so we have n summation y summation x2, then up to summation xk. Okay. Then summation x1, then summation x1y, okay, then summation x1 x2, then summation x1 xk. Okay. So, then this is summation xk, this is summation x1 xk. Okay. This is summation xk squares divided by n summation x1, summation x2, summation xk, then summation x1, summation x1 square, summation x1 x2, summation x1 xk, continue, summation xk, summation x1 xk, then summation x2 xk, summation xk squares. Okay. So, this is how the entire structure. So, that means the beta 1 head coefficient, beta 1 head coefficient will be like this. So, this is what beta 1 head coefficient. So, beta 1 head coefficient is this particular domain by this particular domain. So, similarly we have to calculate the beta 1 head, beta 2 head, beta 3 head, beta k head. So, now by the way we can again simplify in a deviation format the way we have done in the case of trivariate econometric. So, what we have to do here, so in fact it is a very complicated thing. So, the way you will design ultimately by by hand or manual, it is very difficult. So, you have to apply some advanced technique like matrix approach to solve this particular problem very quickly. In fact, you can apply here also. This is nothing but in a you can say matrix format. Even if you like to know the value of this particular matrix and value of this particular matrix, then you can get the beta 1 head. Similarly, you can get the value of beta 0 head. So, in that process, so you will continue like beta 2 head, beta 3 head, beta 4 head, and up to beta k head. So now what is the standard procedure? As usual, you have to calculate beta 0 head is nothing but y bar minus beta 1 head x1 bar, beta 2 minus beta 2 head x2 bars, like beta k head xk bars. Okay. So so first and foremost step is that, so you have to first find out beta 1 head, beta 2 head, and beta k head. The moment you will get these betas, then you will put in first equation where beta 0 head equal to y bar minus beta 1 head x1 bar, beta 2 head x2 bar, and so on up to beta k head xk bar. So the moment you will put all these values, then you will get beta 0 head. So no point to calculate beta 0 head immediately. So you have to calculate the subsequent items. Obviously, within this means with these subsequent items you can have the beta 0 heads. Okay. So this is how you have to simplify this entire procedures. So now what you have to do? So the standard procedure is that if you will simplify further, then it will be coming like this. It can be also deviation format. So ultimately the standard structure is that y equal to beta 0 head, beta 0 head plus beta 1 head x1 plus beta 2 head x2 plus beta k head xk, okay, plus continue. This is beta 3 head x3 and plus continue up to beta k head xk. So this is how you have to proceed. All right. So now the moment you will get all these items, then obviously next step is you have to go for the reliability checking. So that means let us assume that the standard estimated model for this particular multivariate model is like this. So that is y head equal to beta 1 head x1 plus beta 2 head x2 plus beta 3 head x3, okay, up to beta k head xk. So now what is the first objective here? So now we have to assume that we have to observe that these parameters are statistically significant, okay. So and second thing is the overall fitness of the model will be statistically significant. So that means we are not going so much complexity to derive all these beta coefficients simultaneously, since in the case of bivariate modeling, so we have two components, beta 0 head and beta 1 head. In the case of trivariate, it is beta 0 head, beta 1 head, and beta 2 head. So so it is mandatory that you need to have information about beta 0 head, beta 1 head, and beta 2 head. But in the case of multivariate, up to when there is a k independent variables are there and k, you can say k number of parameters are there, then obviously, so in that context it is very difficult to go manually, and it is not practically feasible to calculate independently the beta 0 head, beta 1 head, beta 2 head, and up to beta k head. So we remember one thing, when we have multivariate problems like this, either you go directly to the software or else you have to go, you can say by matrix approach. If you will apply the matrix approach, you can have the results also very quickly. I will highlight a little bit here about this matrix approach, how this multivariate complexity problem can be very simple way, can be analyzed in a very simple way. Okay, so this is I will discuss this concept later. Let me first highlight here the practical feasibility of this particular estimated model. So we have two different objectives here. Once the estimated model with you. So first objective is to know the significance of the parameters. So that is the significance of parameters, okay, and second is the overall fitness of the model, okay, overall fitness of the model. First is the significance of parameters, and second is the overall fitness of the model. So overall fitness of the model, of course it depends upon R square and adjusted R squares. So and it is followed by F statistics. So this is significance of parameter, means all beta 0 head, beta 1 head, beta 2 head up to beta k head are also means we need to have a t beta 0 head, t beta 1 head, t beta 2 head to beta k. beta k head. So this has to be statistically significant. So that means it is the through t statistic we have to follow up the significance of the parameters, and through f statistic we have to signify the overall fitness of the models. Okay. So now so we need two different tables altogether. So I am briefly highlighting here. So if you don't go for this tabular form, then it's better. So what is the usual format of estimation process? So now we have y head equal to beta 0 head plus beta 1 head x1 plus beta 2 head x2, okay, up to beta k head xk. Okay. So we need here variance of beta 0 head, okay, we need here variance of beta 1 head, we need here variance of beta 2 head, we need here variance of beta k head, okay, variance of beta k heads, okay, variance of beta k heads. So followed by t of beta 0 head, t of beta 1 head, t of beta 2 head, and t of beta k heads, okay, t of beta 0 head, t of beta 1 head, t of beta 2 head, t of beta k heads, okay. So then followed by probability level of significance, probability level of significance, probability level of significance, probability level of significance. That means the standard rule is here is that, like bivariate format and trivariate format. So we first get the estimated value of beta 0 head, beta 1 head, beta 2 head, and beta k heads. That means estimated value of all these parameters, kth number of parameters, and followed by you have to calculate the variance of all parameters. So beta 0 head, beta 1 head, beta 2 head, and you can say beta k head. So the moment you will get variance of all these parameters, then you have to go for standard errors. So that is the square root of all these variances. So that is variance of beta 0 head, variance of beta 1 head, variance of beta 2 head, and variance of beta k head. So now the moment you will get the standard error of beta 0 head, beta 1 head, beta 2 head, and beta k head, then obviously you have to set the null hypothesis. That means you have to set the null hypothesis for beta 0 head, beta 1 head, beta 2 head, and beta k head. So that means your null hypothesis is H0 such that beta 0 head not equal to 0, beta 1 head not equal to 0, beta 2 head not equal to 0, and beta k head not equal to 0. Then the alternative hypothesis means against null hypothesis, the alternative hypothesis is that beta 0 head not equal to 0, beta 1 head not equal to 0, beta 2 head not equal to 0, and up to beta k head not equal to 0. So that is how the fitting of null hypothesis and alternative hypothesis. Then by the process, since it is equal to 0, then obviously t of beta 0 head is nothing but beta 0 head by standard of beta 0 head. Then for t of beta 1 head is equal to beta 1 head by standard error of beta 1 head, then t of beta 2 head equal to beta 2 head by standard error of beta 2 head. So you will continue like this up to beta k head. So that means ultimately you like to know what is the t of all these parameters, means t statistic of all these parameters. The moment you have all these parameters, means t statistic of all these parameters, that is your calculated t statistics. Then again you have to compare the tabulated statistic with respect to the number of observations and particularly the degrees of freedom. So that means here we like to see again you have to go by this significance level 1%, 5%, and 10%. So now for instance for beta 0 head you have to see whether the calculated t of beta 0 head is substantially greater than to tabulated t beta 1 head, and if it is so, then at what level is it significant at 1% level, or it is significant at 5% level, or it will be significant at 10% level. So that means you have to go individually for each and every parameters, and the requirement is that each parameter has to be statistically significant. So that means beta 0 head must be statistically significant, means most probably we always expect that this should be significant at the most, means at the highest level. So that means at most at the 1% level. So we are expecting that beta 0 head, beta 1 head, beta 2 head, all these parameters should be statistically significant at 1%. So this is our assumption, or you can say expectations. It may not happen. So if it is happen, then it's very fine. Okay, if it is happen, then we have to see the other side of the problem. That is the overall fitness of the models. That means if all the parameters are highly significant at 1%, then obviously by default R square should be statistically highly significant. Otherwise it will go other way around. So that means if all these parameters are all these parameters are statistically significant, and other side R square is not statistically significant. That means in typically you can say, let's say all these parameters are statistically significant at 1% level, but in the case of R square it is statistically significant at 10%. So then still the problem can be fitted or cannot be considered as the best model for forecasting or policy use. So that means the standard structure is that if all these parameters are statistically significant at 1% level, then in the other side R square should be statistically significant at 1% level. Otherwise, if it is 1% levels and if it is 5%, this is okay, but still the model cannot be called as a best fitted models. But in reality, it's very difficult to find a situation, particularly for multivariate problems, where all these parameters are highly statistically significant. So that means it is very difficult to find a situation where all these parameters are statistically significant at 1%. So there is a lots of ups and downs. That means if few parameters are statistically significant at 1%, few parameters are statistically significant at 5%, and few parameters are statistically significant at 10%, or there may be chance that few parameters are also not statistically significant. The model may be very accurate, may be practically, I cannot say practically feasible, but it will be more justified if few means this type of structure must be there in the model, means most of the variables are statistically significant at a higher level, then followed by few are at the medium level, that is at the 5% level, and few are also at the 10% level, that is at the lower level, and few parameters, say 1 or 2, should not be statistically significant. If such type of model is in front of you, then it will be considered, or it can be practically true. But in other case, if all these parameters are statistically significant, then yes, this model is no doubt about it is considered as the best model and can be used as forecasting, but still there is a strong doubt about this type of models, and for that, before using that model for forecasting and policy use, you have to go through very carefully once again, with respect to problem setup, data entry and estimation, and also the significance choice, means criteria, whether this is okay or not. So then you have to say that yes, this is the correct model, and it can be considered as the best models, and it can be used as a policy use, and you can say forecasting. But if majority of the parameters are not statistically significant, but R square is you can say highly significant, then the problem has a lots of problem, and that is most natural sometimes. For instance, R square is usually calculated with the ratio between exponent sum square by total sum square. So total sum square is always same, whether you are in the bivariate format or trivariate format or multivariate format. If you include one independent variable, whatever PSS you will get it. For instance, we have a y information. Then in the first problem we have y x1. In the second problem, same y with the x1 x2. Okay, so y x1. Then in the second case, the same y x1, then we add another variable x2, then we take a third case. So same y x1 and x2, then we put another variable x1 x3. So this is how you have to proceed one after another. So if you proceed like this, y with the 1x1 and y with the 2x1 2x and y with the 3x like this, then obviously in each case the summation y square is always constant, because we are copying and pasting the same y value everywhere in this particular setup. Okay, so obviously if you compare in all cases, then summation y square is always equal, whether it is a bivariate problem, whether it is a trivariate problem, or whether it is a multivariate problem. So that's why there is a possible chance that a few parameters are not statistically significant, or you can say most of the parameters are not statistically significant, or significant at the very lower level, but R square will be statistically significant at the higher level. In this particular context, the modeling is very interesting, because by means you have to assume that this model is not considered as the best model. So as a result, you have to again go for rotation or reformulation, etc., till you get the best fitted models. Of course, it is a very continuous process, and in fact, in the multivariate case, the complexity or the process is very volatile, or you can say very flexible in nature. So it depends upon the situation, setup, and problem information. So now accordingly you have to see the situation and find out the best model for you. So that means the degree of decision making is very high in the case of multivariate model econometric modeling. So in that case, there are number of constraints with respect to x, and various side problems are there before you handle this particular model, or before you call that the model is the best fitted model. So this is one part of the story with respect to specification of the parameters. The second part of the story is that we need to have, this means it is the question of overall fitness of the model, overall fitness of the model. So that is as usual. So you have sum squares, so means first is sources of variations, then sum squares, then mean sum squares, then then you can say degrees of freedom, then of course f statistics. First will be R square, then f, then will be probability value of significance. This is how you have to proceed. So this is nothing but explained sum square, this is residual sum square, this is you can say total sum squares. Okay, so as usual the structure is more or less same. So this is otherwise called as a summation y hat square, this is summation e square, this is summation y square. Okay, so obviously this is summation y hat square by k minus 1 here. So here if it is k, then obviously k minus equal to 0. So obviously there will be some gap here. Okay, so summation y square is also divided by number of freedom, and summation y square by obviously it is n minus 1. Okay, so this should be n minus k. So we have to see some degrees of freedom here, because we are considering here k as the total number of variables. So obviously it will be little bit complex, but let's say there is a model up to, you can say m, then obviously you will find out k minus m. So okay, so this is how the degrees of freedom. That means that means we have to see what are the degrees of freedom for this particular context. Means in this particular context, degree of freedom is very important, because it is a multivariate problem. So right, so so this is R square ESS by TSS, and obviously F is ESS by RSS. Okay, so similarly this is nothing but summation y hat square by summation y square, this is summation y hat square by summation e square. Okay, so this is how you have to proceed. So this particular structure is like this. This is summation e square. So this is the structure of particularly called as overall fitness of the model, and otherwise it is called as a ANOVA test. Okay, analysis of variance. It is called as a analysis of variance. It is called as analysis of variance, where there are three standard components is very important. That is explained sum square, residual sum square, total sum squares, and followed by summation y hat square, summation e square, summation y square, and corresponding with the help of degrees of freedom we have to calculate the R square and F statistics. Okay, so most probably in the case of multivariate model, R square should not be very less. By default it will be very high, because number of x variables are substantially high. So as a result, most of the multivariate cases you will find R square is substantially high. but the major difficulty is that, or major problem is that you may not get all these parameters are statistically significant, but reverse is always true. That means there is enough chance that R square will be highly significant, and you can say parameters are not, all parameters are not statistically significant, but by default R square will get high, and obviously it can be, there is enough chance that it may be significant, but in the same times you can say your significance of parameter may not be true. So, see, there may be few are significant, there are few may not significant at lower level, or there are certain situation there are statistically insignificant. That means there is also chance that all parameters may not be significant. So, while R square will be very high, but R square high does not mean that it is significant. So, it has to be checked through F statistics, because when R square is high with respect to the involvement of independent variables, then obviously we need to calculate first adjusted R squares. Okay, so which is the which is considered as the best indicator rather than R square. But whatever components you will use, R square or adjusted R square, it has to be tested. So, obviously we have to go for this F statistics. So, the moment you will go for F statistics, so F statistic is always followed by degrees of freedom. That means we have not mentioned here the degrees of freedom. There is a degrees of freedom here, and there is a degrees of freedom here. So, we have to find out the degrees of freedom. Then with the basis of this degrees of freedom, the significance of R square may be, you can say, it may affect, but by and large R square will be substantially high. Whether it is significant or not, that depends upon the sample observations, because yes, of course, the situation is very interesting when number of samples are also very high, number of variable setups are very high. Then in that case there is enough chance that R square will be substantially high, and in the same time F is statistically significant. This is okay, but in the other side majority of the parameters are not statistically significant. So, in this particular setup it is okay if the sample observation is true enough, then this involvement of variables, means particularly independent variables. So, you will get both high R square and both high value of F statistics, but in the same times there is, means it is not mandatory that if you will get high R square and high F value, that all these parameters in this side will be statistically significant, but the reverse is always true. Reverse is always true means that if you if all the parameters are highly statistically significant, then there is a possibility of 99% chance that you will get this R square and F statistic is both are statistically significant. So, in that context you have to find out you have to formulate a problem in such a way so that both can be go simultaneously. That means all these parameters has to be statistically significant, and it's not mandatory that it should be significant, or all parameters should be significant at 1% level. Even if you are 1% level, if you are 5% level, if you are 10% level, does not matter, but should be majority of the parameters should be statistically significant, and R square will be statistically significant. But if you find a particular situation where few are statistically significant at the higher level, few are statistically significant at the lower level, and few are non-significant, in other side R square is high and F is statistically significant. So, here there is a there are two methods or two criteria here to choose the best fitted models. There is a technique called as a stepwise regression. So, stepwise regression, if you will go one by one, then it means step by step you will get the model which is absolutely best for this forecasting or policy use. The the problem is here that the moment you will get a model, estimated model, where few parameters are statistically significant and few parameters are not statistically significant, then in that context what happens, the variables which are not statistically significant may be or can be dropped, okay, in the present context. So, now so let us assume that there are 10 variables in the system. That means if k equal to 10, So let us assume that there is a few variables, say x7 or x6, is it not significant. So what you have to do, you first drop x6, then you estimate the model and you check whether after dropping x variables, other variables are statistically significant and R square is high and also it is highly statistically significant. Then if it is okay, then it's fine. Okay, otherwise you drop x7s, then you again estimate the models and you check all these parameters, relevant parameters should be highly statistically significant and R square will be high, then followed by F is also statistically significant. Okay, if it is, if you will get the all these parameters are highly significant after dropping x7 and in the same time R square and F are very high, then that is considered as the best model for forecasting and policy use. But by the way, if you drop x6 or x7, if other variables are insignificant in the same time, then there is again problem. The problem is more complex. For instance, some variable may not statistically significant, but it has a substantial integration or you can say connection to other variables. That means some variables may indirectly influence and that has a significant impact on y. So now if you drop that particular variables, then obviously the impact of the additional variable means previous variable, say x3, will be get hampered. So that means x3 may not be significant, but if you add, if you include x6, then obviously x3 will be active and it will influence on y. So this type of problems basically, or you can say you have to face in the case of multivariate model. So that is how multivariate problem is very complex problems, and it is very it is in fact very serious challenge to analysts or researchers, particularly those who are estimating or analyzing the particular problem, or you can say analyzing the data setup. So we need a situation or we need a problem or information. By the way, we have to get the estimated model, and that model means the way we will estimate the model, most of the cases all these parameters should be statistically significant, and you can say R square and F should be substantially very high. But if out of which if few variables are highly significant and few variables are not significant, then in that case you have to check, cross check by dropping this variable whether there is any kind of improvement in the rest of the models. Okay, for instance, if you are dropping x6, then rest of the item x1 up to x10 means without having the x6 involvement, and obviously R square and F. Then you check the model. So that means like this. So what you will do here is you have three different sorts. Let us say y is x1 up to x2 up to x10. Okay. So now by the way, okay, I will write it here: x3, x4, x5, x6, x6. This is x7. Then let's say, okay, this is x5, this is x6. Okay, we will take x7 years. X7 years. All right, it's better. I will write it once again. Y equal to x1, x2, x3, x4, x5, x6, x7, x8, okay, x9, x10. Okay, let us assume that the model consists of one dependent variable y and 10 independent variables, that is x. Okay, so now you go by estimation process. By the way, this is significant, 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 and this is not significant. Okay, let us assume that this is not significant, this is significant, then this is significant, and this is not significant. Okay, and this is significant. R square is by default is very high, and F is also default very high. Okay, this is by default it's very high. So now this model can be practically considered as the best models, particularly considered as the best model. Still, for your feasibility part of the concern, or you can say reliability part is concerned. So what you have to do, you make an experiment. Okay, so this is, you can say, original case and you call it case 1. So what you have to do, you go to case 2, you know what you have to do, you take models y equal to x1, x2 up to, you know, x1, x2, then x3, x4, x5 dropping x6, okay, then x7, x8, x9, x10, okay, check it the model status. Then case 3, you take another case y equal to x1, x2, x3, x4, x5, x7, x8, and then x9 is dropping here, then it is x10, okay. So now there are 3 different cases. So what you have to do, this is already in front of you, so you have to go for this estimation and you check the R square value and the significance of these parameters. So by dropping this variable, if the significance of these parameters are relatively very high level of significance, and R square is relatively high and F is relatively high, then that will be best considered as a best. Otherwise, if it is affecting the significance level at the lower level, then it is better to reject this particular case 2, and you then you proceed to case 3. By case 3, you have to again re-estimate the model. Then by the drop, means by the process of dropping x9, if all these parameters significance level is relatively high and R square F is relatively high, then again you means it is considered as the best model to case 1s, okay. But by the means by the process of dropping x9, if you know x1, the significance of other variables will be drastically reduced and R square F is drastically reduced, obviously R square will not R square will reduce because we have already dropped one variable, but we have to check whether this R square is, you know, adjusted R square is relatively okay and F is statistically significant and other variables level of significance is also relatively high. If it is okay, then it is considered as the best fitted model than case 1. So if it is not okay, means after dropping this variable, suppose a few other variables are, you know, its significance level is lower level than the original case, then it's better you remove this case 2 and case 3, you go ahead with the case 1. So that means even if in the case 1 two variables are not statistically significant, that will be considered as the best model and can be used for forecasting, okay. So this is how the basic problems you have to face in the multivariate models. These are lots of complexity, so that complexity you have to work out. There are various or trial error and methods you have to apply to get the model best fitted, okay. So either you redesign the models, restructure the models, then reformulate the data setup, reformulate the problem setup till you get the best fitted model. So whatever you know structural change you have to do, so all these cases the model you know estimation information may be different, okay. Most of the cases it will be unique, means very rare case it will be unique, but most of the cases you will find the difference of results, okay. So if you will change the setup, so ultimately we are going for experiment to get the best fitted model. So now in addition to that, you will face lots of different complexity, like you know variables inclusion and exclusion. So it is very interesting game so far as a regression technique called as a stepwise regression. So by this you know technique we can get to know, means if you go by stepwise technique, then it is you know first you have to track which particular variable is the most important variable. That means that you have to target with the help of t value. So we quickly make a look with respect to all these parameters coefficient, then we have to find out the t statistics. Then if the t statistic of a particular variable say x5 is substantially higher than the other t statistic, then we have to include first that first step, okay. So that is how the process of stepwise. Then you have to collect R square and F, then you enter the next highest t value, okay. So that variable has to be included. So again you have to check R square and F. R square will be very high substantially, okay. So once you move one by one, but in the same time you have to check the F statistic, but in the same time you have to see the variable should be significant equally. Then you add third highest variables, then by the way all these variables should be significant and R square will be high, F will be substantially high. So you continue this process till you get the best fitted model, and you have to end in that particular point where the inclusion of a particular variable will not you can say improve anything about R square f or significance of the parameters. So that is the criteria through which we have to judge a best models in a multivariate case. So multivariate case is a very complicated case, very, in fact, in sometimes it's very interesting because it gives lots of structural frameworks through which you have to go here and there to get the best fitted models. So with this we will conclude this sessions. So in the next class I will discuss the matrix approach of this multivariate modeling. So the way we have discussed here, in fact it is very much related to simultaneous equation format without having means direct touch of matrix. But in next class I will discuss a format where by the beginning we have to apply matrix and we can conclude with the matrix, so that it will be very easy and you can get the answers very quickly. Even if by the matrix approach multivariate problem, you can in the class itself you can solve that particular problems. Okay, so it's a very interesting game. So we'll discuss this detail in the next class. Thank you very much. Have a nice day.